In this session, we'll explore large language models LLMs with a focus on generative pre-trained transformers GPTs and their groundbreaking impact on natural language processing. Previously, we discussed transformer-based architectures and how they revolutionized language understanding. Today, we are taking it a step further by looking at large language models, how they are trained, their capabilities, and their real-world applications. We'll break down the concept of pre-training and fine-tuning, understand how GPT models generate human-like text, and explore their use in applications like chatbots, content creation, and code generation. By the end of this session, you would have a solid understanding of how large language models work and how they can be leveraged for various natural language processing tasks. Let's get started.
Hello and welcome. In today's class, we'll be looking at large language models, LLMs, and in particular, we'll be emphatic on generative pre-trained transformers, GPTs. Here is the outline of what we'll cover in this session. Overview of large language models, LLMs, and in particular, generative pre-trained transformers. Key applications of GPTs. And as always, we'll look at practical use of the Hugging Face Transformer library, where we'll fine-tune pre-trained models for custom NLP tasks. By the end of this session, you will be able to explain large language models, LLMs, and their roles in modern natural language processing. You will also be able to identify practical applications of GPT in text generation. You should also be able to utilize the Hugging Face library to load and fine-tune pre-trained models and be able to implement a fine-tuning workflow on custom datasets for NLP tasks. Before diving into large language models, let's understand what a language model is. A language model is a machine learning model that predicts the next token in a sequence based on the context. Tokens can be words, part of words, or characters. The most famous language models are smartphone keyboards that suggest the next words based on what you've currently typed. For example, in the sentence, the cat sat on the. So a language model tries to predict what the most likely word would be. It could be mat, it could be anything. So for example, it could predict that the next word is mat. This notation represents how a language model works, and it's usually read as the probability of the word mat occurring given the context the cat sat on the. So basically, the model uses the prior words to predict the most likely next word. And by analyzing patterns in its training data, the model assigns probabilities to possible next words. For example, it might assign a higher probability to the word mat than to other unrelated words like banana, for example. This process enables the model to generate contextually appropriate text. This formula represents the core principle of how language models operate. So the probability of the current token xt occurring given all previous tokens x1 to xt minus 1. It means that the model predicts the next token xt. It means the sequence of tokens that came before it. This autoregressive property enables the model to generate coherent text as each prediction depends on the context established by earlier tokens. For example, if the prior tokens are the cat sat on the, then the model evaluates the probabilities for the next word based on the context. And it does that by prioritizing likely options like math that we've seen in the previous example. Now, having understood what a language model is, what's a large language model? A large language model, LLM, is an advanced AI system trained on massive datasets to understand and generate human-like text. Key features include language understanding, where it captures meaning and context from text, contextual generation, where it produces coherent and contextually relevant responses, and applications in diverse fields, because LLMs are used in several applications including chatbots, translations, summarization, content creation, and more. Large language models have evolved significantly over the years. Early NLP models like Word2Vec and Glove focused on capturing relationships between words as static embeddings. Recurrent neural networks or RNNs brought sequence-based modeling but struggled to handle long-term dependencies in text. The introduction of the transformer architecture in 2017 marked a major shift. Unlike recurrent neural networks, transformers efficiently process text in parallel and capture long-range dependencies, which make them ideal for tasks like machine translation using the encoder-decoder framework. Key milestones include BERT, introduced in 2018, which focused on understanding text using a bidirectional encoder. That same year, GPT emerged, pioneering text generation with a decoder-only transformer. Together, these advancements set the stage for today's large language models. There are several prominent large language models shaping the AI landscape today. For example, we have the OpenAI GPT series. This includes GPT-2, GPT-3, and GPT-4, which have progressively improved in scale, capabilities, and reasoning, becoming benchmarks in generative AI. We also have Google's Palm and Gemini. Palm, or Pathways Language Model, is designed for multitasking and excels at diverse applications. Gemini goes a step further, integrating real-time data capabilities with LLMs. We also have Anthropic's Cloud. This model prioritizes safety and explainability, making it suitable for ethical AI applications. We also have the Meta's Llama, which is a lightweight and open source application. Llama is optimized for accessibility and efficiency, particularly in research and low resource settings. Other innovations include GPT-Neo and GPT-J from Elotha AI. It provides open source alternatives for text generation. We also have Bloom from Big Science, which supports multilingual tasks addressing diverse language processing needs. These models collectively represent the diversity and rapid advancements in large language model technology today. The transformer architecture, introduced by Vaswani et al. In 2017, in the paper Attention is All You Need, is the foundation for most large language models. Unlike previous sequence models like recurrent neural networks or LSTMs, transformers do not process data sequentially. Transformers are the default building blocks for NLP today. The original transformer model consists of two main components, an encoder and a decoder. Each of these is built as a stack of transformer blocks. This design was particularly effective for machine translation, where the goal is to convert text from one language to another. The encoder processes the input sequence, capturing its meaning and context, while the decoder generates the output sequence in the target language. The encoder-decoder architecture became a natural fit for translation tasks because it allows the model to understand and recreate text across different languages with remarkable accuracy. This foundational structure paved the way for the evolution of many transformer-based models. The key feature of the transformer architecture is the attention mechanism capabilities. There are three main types of attention mechanisms used in transformer models, each serving a different purpose in processing input data. We have the encoder self-attention. In this mechanism, each token in the input sequence pays attention to all other tokens in the sequence. The purpose is to understand the relationship between words in the context of the entire sequence. It helps the model to build a more complete representation of the input data. We also have the masked decoder self-attention. In the decoder, self-attention is performed in a masked manner. This means that each token can only attend to previous tokens in the sequence, not future ones. This is crucial during training when the model is generating tokens step by step, as it simulates the autoregressive nature of text generation, predicting the next word based on previously generated words. We also have the encoder-decoder self-attention. This type of attention occurs between the encoder and the decoder. The encoder processes the input sequence and generates a representation of it, which is then passed to the decoder. In this stage, the decoder attends to the entire encoded input sequence, enabling it to use the context of the entire input while generating output tokens. These attention mechanisms are fundamental to the transformer architecture, allowing the model to understand context and generate meaningful predictions. Transformers have become the go-to architecture for natural language processing today because they handle the complex relationships in text so well. Now, let's focus on the encoder part. Encoders like BAT, Rubata, and Cybat are designed to capture bidirectional context. This means they understand both the left and right context of a word in a sentence, giving them a deeper understanding of the meaning. This bidirectional approach is a key strength of these models, allowing them to perform tasks like text classification, quest answering, and more with high accuracy. Moving on to decoders, for example, the GPT series, which fall into this category. These are also called causal or autoregressive language models. The key feature here is that they generate text one word at a time, predicting the next word based on previous ones. This makes them very natural for tasks like text generation. However, a limitation is that they can't see future words during training or predictions. They can only condition on the words they've already generated. This makes them less suitable for tasks that require full context like text understanding compared to encoders. Finally, we have the encoder-decoder models. These models combine the strengths of both the encoder and the decoder. The encoder first processes and encodes the input, and then the decoder generates output based on this encoded information. This setup is perfect for conditional generation, where the output depends directly on the input, like in machine translation or summarization. It allows for a more flexible and powerful approach compared to just using a decoder alone, as the model can now generate contextually relevant output from a wide range of inputs. Let's understand the difference between autoregressive and non-autoregressive models. In non-autoregressive models, the input and the output are treated as separate sequences. For example, in tasks like part-of-speech tagging. Each word is assigned a label independently. There is no sequential dependency between the inputs and the outputs. Each word is processed individually. On the other hand, autoregressive, or what we call causal models, such as GPT, uses a sequential approach. Each output is fed back as the next input so that the model generates tokens one by one, with each new token depending on the previous ones. This is ideal for tasks like language modeling or text generation, where the goal is to produce coherent and contextually relevant text step by step. Now, back to the business. Like I mentioned, the transformer model marked the start of the LLM era in 2018, revolutionizing how we approach natural language processing. First, BART was introduced in October 2018 and is focused on representation. It used a bidirectional approach to capture context from both directions of a sentence, and this makes it a powerful tool for tasks like sentiment analysis and question answering. Then the GPT was released in 2018, June specifically, and is focused on generation. Unlike BART, GPT used a unidirectional approach, and it excels in text generation tasks, where the model predicts the next word based on previous ones, as we see in chatbots or story generation. Together, these two models set the stage for the advanced large language models we use today. So a large language model can be an encoder-only model, a decoder-only model, or an encoder-decoder model. Each of these models serves a specific purpose based on whether the task is more about understanding, generating, or both. For example, BART and its lightweight version, DistilBART, are key examples of an encoder-only model. These models excel in understanding text by capturing bidirectional context, making them great for tasks like classification and question answering. The GPT series are classic examples of autoregressive models that are classically decoder-only models. These are focused on generating text where each word depends on the previous ones. They are great for tasks like text generation and language modeling. Models like T5 and MT5 combine both encoder and decoder components, allowing them to handle tasks that require both understanding and generation, such as in machine translation or text summarization. Let's now focus on the Generative Pretrained Transformers, or GPT. It was introduced by OpenAI. It is a decoder-only transformer model primarily designed for text generation and next word prediction. GPT excels at producing coherent and contextually relevant text by predicting the next word in a sequence based on prior words. GPT is similarly motivated to BERT, but with a different design. Both aim to leverage large amounts of unlabeled data to pre-train a language model, and the idea is to help the model understand general patterns in language. While BART uses a bidirectional approach for understanding, GPT uses an autoregressive approach, focusing on generating text and predicting the next word in a sequence. For GPT's pre-training, the model was trained on large datasets like book corpus and English Wikipedia, which provided a diverse range of text. The pre-training task is simple but powerful. The model predicts the next token given the previous tokens. This task provides more learning signal than BERT's masked language modeling, as the model learns to generate coherent sequences by understanding word dependencies. As for the pre-training results, the original GPT had 117 million parameters and performed similarly well on benchmarks like Glue and Scott, showing strong capabilities in language understanding and answering questions. Let's now walk through the GPT family, which has evolved significantly over the years. We have the GPT-1, which came about in 2018. This was the beginning of the generative pre-training concept. Like I mentioned, it had 117 million parameters and has showed that large-scale pre-training on unlabeled text could improve performance on downstream tasks. It also introduced the idea of pre-training followed by fine-tuning for better results. The GPT-2 was introduced in 2019 and expanded the scale with about 1.5 billion parameters. It demonstrated the power of scaling language models and achieved state-of-the-art performance across multiple tasks without task-specific training. It also brought attention to the potential and risks of AI text generation, sparking ethical discussions about its use. The GPT-3 came about in 2020 with about 175 billion parameters. GPT-3 took the leap into few-shot learning, showing it could perform well on various tasks with minimal examples. This marked a turning point in AI research, popularizing large language models as general-purpose tools across diverse applications. The GPT-4 was introduced in the year 2023 and has improved on GPT-3 by incorporating visual input processing, stronger contextual reasoning, and enhanced safety measures. Its parameters remain undisclosed, but it is believed to be significantly larger than GPT-3, with some rumors suggesting that it has about 1.76 trillion parameters. Let's now break the anatomy of a GPT model. We start with the input embedding, where the model begins by converting the input tokens, whether they are words, subwords, or even characters, into what we call dense vectors. These vectors represent the semantic meaning of the tokens, making them understandable for the model. Since the model processes data sequentially, we need to add positional information to the embeddings. And this ensures that the model understands the order of words, which is crucial for tasks like language generation. The core of GPT is made up of multiple transformer blocks that are stacked together to form a deep architecture. These blocks include two main components: the multi-head self-attention mechanism and the feed-forward neural network. The multi-head self-attention allows the model to capture relationships between words, even if they are far apart in a sentence, and they do that by calculating attention scores. After attention, this network processes the output to perform deeper feature extraction and then enhance the model's understanding. We also have the residual connections and layer normalization. These mechanisms help in stabilizing gradients during training and improve convergence. They allow the model to efficiently train without getting stuck in the optimization process. Finally, the output layer generates the model's prediction. For autoregressive models like GPT, this could be predicting the next word or token in a sequence based on the previous context. And this architecture, with its attention mechanisms as well as the deeper layers, is what gives GPT its ability to generate coherent and contextually aware text. Let's now look at the architectural overview of a GPT model. The key process actually is the autoregressive generation, which involves predicting one token at a time based on context. For example, when prompted to recite the first law of robotics, GPT-2 generates one token at a time. So it processes each subword masking future words, and then attending only to the previous ones. And this autoregressive method allows for text generation. This in contrast to BERT, which uses encoder blocks and is designed for text understanding and classification. So this is the output. Like I mentioned, the models work through a process called autoregression, and after each token is produced, it is added to the sequence of inputs, and then the updated sequence becomes the input of the next step. So this allows the model to generate text step by step with each new token conditioned on the previous ones. This concept is similar to what made recurrent neural networks highly effective in language modeling. The first GPT model, what we call GPT-1, was pre-trained on the book corpus, a large dataset containing text from a variety of books. The architecture of GPT-1 laid the foundation for later models because it introduced the idea of pre-training on vast amount of unlabeled text and then fine-tuning on specific tasks. This approach significantly improved performance on downstream NLP tasks, making it a breakthrough in large language modeling. Now, GPT-1 also demonstrated the effectiveness of fine-tuning for specific end tasks. So if you read the paper, after pre-training on a large corpus, the model was fine-tuned for various tasks where both input and output are converted into text. Some examples include tasks like classification, entailment, similarity, and multiple choice. Fine-tuning allowed the model to specialize in these tasks and improved the performance significantly compared to what we have in traditional models. Now, GPT-2 is very similar to GPT-1, but with a few key improvements. First, layer normalization was moved to the input of each subblock for better stability. And then the vocabulary was also expanded to 50,257 tokens, and also the context size increased from 512 to 1024. And this allowed the model to handle longer sequences. GPT-2 was trained on a massive dataset of 8 million documents from the web, specifically using common crawl but excluding Wikipedia. These changes made GPT-2 to be significantly more powerful and capable of handling diverse tasks. GPT-2 comes in various model sizes, each with increasing capacity and performance. These include the GPT-2 base, the GPT-2 medium, the GPT-2 large, and the GPT-2 extra large. The GPT-2 base is a standard model with 117 million parameters. The medium has 345 million parameters and offers better performance. The GPT-2 large is equipped with 762 million parameters, and this version delivers more accurate results. And the most powerful variant is the GPT-2 extra large with 1.5 billion parameters, providing the best performance across tasks. Each increase in size allows the model to capture more complexity and improves its ability to understand and generate text. Now, GPT-3 is a massive leap forward in language modeling, introduced in 2020. It features more layers and parameters, and this significantly increases its capacity to learn and generate text. Was also trained on bigger datasets. It's trained on diverse and extensive text from the web, and also has longer training duration, allowing the model to fine-tune its understanding of language. It also has larger embedding, hidden dimensions, which helps the model capture more intricate relationships in the data. It also has a larger context window, which enables it to handle longer text sequences and capture broader context. These improvements made GPT-3 one of the most powerful language models at the time. Now, the language model of GPT-3 is so effective at writing naturally because of its scale and training. It has been trained on an enormous amount of text from diverse sources, and this allows it to understand context, capture nuances, and mimic various writing styles. The large number of parameters helps it generate coherent, relevant, and contextually appropriate responses. To enhance the learning process, we can augment the dataset by modifying the text example. For example, here we can create valid learning data from the prompt. For example, if the input is second law of robotics, and then the correct output is going to be A. And then if we change that particular input to include A, then what we get as the output will be now robot. And when we now include robot as part of the input, then what we get as output this time around is going to be another word, must, isn't it, based on the wordings of the text, second law of robotics, a robot must obey the orders given to it by human beings. So by generating a large number of these modified examples, we can expose GPT-3 to a broader range of data, and this helps in improving its ability to understand and predict text in different contexts. This technique helps in fine-tuning the model for specific tasks and better performance. So even with its high precision, GPT-3 can still make mistakes during learning. So the model repeatedly calculates the error between its incorrect predictions and the correct answers. And through this process, it learns from its mistakes, adjusting over millions of iterations to improve its accuracy and text generation abilities. This iterative learning is essential for refining the model's performance. GPT-3 encodes its knowledge into the about 175 billion parameters. Initially, these parameters are in a random state, but through the learning process, they get adjusted to values that allow the model to make highly accurate predictions. So as the model processes more examples, the parameters are fine-tuned, and this enables the model to generate more relevant and precise text based on the learned parameters. GPT-3 does not process entire strings of text at once. Instead, it processes each token individually. A token could be a word, part of a word, or even a character. This token-based processing helps the model handle text more efficiently. The underlying structure of GPT-3 is based on concepts from Google's language model, which also uses a similar tokenization approach for better handling of language and context. GPT-3 can handle 2048 tokens, which is a significant increase from GPT-2's 1024 tokens. This expansion allows the model to process longer sequences of text and helps in capturing more context. One key example is the path from the word robotics here, the sixth column. So to the word A here. This highlights how the model tracks and processes relationships between tokens over a longer span of text. And this improvement reflects GPT-3's ability to manage more complex and nuanced language patterns. Now, the first step in predicting the next token involves embedding, where GPT-3 converts the input text into a vector representation. In addition, position encoding is added to this vector to indicate the position of each token in the sequence. In the second step, the model performs prediction calculations based on this vector input. Finally, in the third step, the output vector is converted back into word, and then this completes the prediction process. This series of steps ensures that the model understands both the meaning and the sequence of tokens it processes. Now, In GPT-3, word token embeddings refers to the process of converting individual tokens into dense vector representations. And these individual tokens could be words, subwords, or even characters. The model uses a vocabulary of 50,257 unique tokens, and each token is mapped to a specific embedding vector. These embeddings help the model understand the meaning of the tokens in a numerical format, and this allows it to process and predict text effectively. In the first stage of processing, each token is converted into a vector through embedding, and then its corresponding position encoding is added to this vector. The position encoding helps the model understand the position of each token in the sequence and ensures that the order of words is reflected in the processing. This combined vector is then passed to the next stage for further prediction processing. Now consider the sentence, "A robot must obey the order given it." In this sentence, understanding words like "it" and such orders requires knowledge of the context, which is where GPT-3's self-attention mechanism comes into play. Self-attention allows the model to assess how each word in a sentence is related to others, even if they are far apart. It calculates a score for the relationship between tokens and expresses this relationship in vector form and helps in adjusting the word representation accordingly. This way, GPT-3 can capture the background and context of the language, making sense of complex references like "it" and such others. The key difference between GPT-2 and GPT-3 in terms of self-attention is the alternating use of dense and sparse self-attention. In dense self-attention, each token's output is influenced by all previous tokens, but the output does not affect the next input until all the inputs are processed. Once the input phase is complete and the prediction phase begins, the output begins influencing the subsequent inputs. This mechanism helps GPT-3 handle context better and allows it to make more informed predictions. In GPT-3, self-attention is performed in a masked manner, meaning it only considers the tokens that appear before the current tokens in the sequence. This is known as causal or masked self-attention. It prevents the model from peeking ahead at future tokens during training, and this ensures that the predictions are made based on the previous tokens only. On the other hand, BERT performs bidirectional self-attention, meaning it considers the entire sequence, looking at both past and future tokens for each word. This allows BERT to understand context from all directions, and this makes it more effective for tasks like question answering and sentence classification. GPT-3 has 96 decoding layers, which is double the 48 layers of the largest GPT-2 model. These layers are responsible for processing the input in a series of stages. In the second stage, the model produces a vector that represents the predicted token. In the third stage, this vector is converted into a word, completing the word prediction process. The increased number of layers in GPT-3 allows for more complex and nuanced predictions compared to GPT-2, enhancing the model's overall performance. In GPT fine-tuning, the model is trained on task-specific data by presenting it in a continuous stream. The input is formatted as a prompt that guides the model to perform specific tasks such as question answering, translation, or summarization. So by adjusting the model's parameters during this process, GPT can learn to better handle particular tasks and helps in improving its performance for specific applications. Fine-tuning helps the model adapt to new contexts, making it more efficient and accurate in generating relevant output for specialized tasks. Fine-tuning GPT-3 enhances its performance on specific tasks by adjusting the model's parameters based on task-specific data. This process allows the model to adapt to different contexts and domains and helps in improving its accuracy and efficiency in generating relevant outputs. So by tailoring GPT-3 to particular applications, its potential for handling diverse challenges becomes even more powerful and also allows for more specialized and effective use. Now, GPT-4 is built on a transformer-based architecture, even though many of its detailed workings remain a mystery beyond its basic structure. It is estimated to be about 15 to 30 times more expensive to run than GPT-3, suggesting that it is much larger and more complex in size. It also offers enhanced capabilities for processing and generating text. Before we end, let's look at some limitations of generative pre-trained transformers. Number one is hallucination. GPT models can generate plausible sounding information that is false or fabricated. There is also this sensitivity to prompts. The output can vary significantly based on slight changes in the input prompt. Also, running large language models like GPT-3 and GPT-4 requires significant computational resource and energy. And there are also ethical concerns. The models can unintentionally generate misleading or false information. And there is this issue of bias and fairness, where GPT models may reflect biases present in the training data, and this can lead to biased or unfair responses. Before we had LLMs, there were a few key processes we focused on. What we focused on was feature engineering, model selection, transfer learning, and of course, overfitting and generalization. With the advent of LLMs, things have shifted to pre-training and fine-tuning, zero-shot and few-shot learning, prompting, and of course, interpretability and explainability. Pre-training and fine-tuning have become key because they allow us to leverage massive amounts of unlabeled data that were previously underused. And the zero-shot and few-shot learning have enabled models to perform tasks they haven't been specifically trained on, just by providing minimal examples or instructions. And also, prompting has become a powerful tool where we describe tasks in natural language and allows the model to understand and execute them. And then also, interpretability and explainability have gained more attention as we try to understand how these models work internally and make their decisions. It is time for our practical walkthrough in Python.
So in this particular lab, we are going to demonstrate the process of fine-tuning a pre-trained GPT-2 model to perform text summarization. And we are going to use a very popular dataset called the CNN Daily Mail dataset. And as usual, we're going to start by installing the necessary modules. That's what we have here, where we are installing transformers, which provides pre-trained models and tools for NLP tasks. We are also installing datasets, which loads and processes datasets like the Daily Mail datasets and the convolutional neural network that we're going to be training. And also we're installing Touch, which is the PyTorch framework for deep learning. It's already installed, but just for us to confirm that everything is fine, we run this, and it tells me that the requirement is already satisfied. So we move to the next stage, which is importing the required libraries. Okay, so from here we are importing load dataset from datasets, okay, which enables us to fetch datasets. And also from here we're importing the GP2 tokenizer, the GP2 LM head model, the trainer, the training arguments, the data collector for language modeling, and we are also importing touch. The GPT-2 tokenizer and the GPT-2 head model are used for the GPT-2 model, and then the trainer and the training arguments are used for model training. And then this one, what we have here, the data collector for language modeling, is for batching. So we simply run this code to import the required libraries. I'm running this on Google Colab, so just to ensure that everything is fast. It's still running, so let's just wait for it to finish. So it has finished. So the next stage is now to load the CNN/Daily Mail dataset, which contains news articles and their summaries. So we want to fine-tune the GPT-2 model for a specific dataset of our choice so that it can be able to do custom tasks. And this particular dataset is the CNN Daily Mail dataset, and this is where we load that particular dataset. So we can just simply run this. Okay. It's still loading. Let's just wait for it. It's still loading, so we have to be patient. Let it finish. It's still loading. So okay, it's done. So let's now display a sample from the training dataset, because this is an inbuilt dataset that we are using for our experiment. So we would like to print a few samples from the datasets. In fact, we're just printing we're fetching and printing the first article and its summary, because indexing in Python starts from 0. So we are fetching the first data point as well as a summary. So we can just simply run this particular code. It will fetch us the first training summary and then the corresponding, the first training data point and the corresponding summary. So we have the sample article, London, England, Reuters, Harry Potter, Star Daniel, blah, 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 gains access to a reported. It's a very lengthy article, as you can see it here, it's a very lengthy article. And from the dataset, this is the summary of that particular, sentence, or rather, sample that we have already loaded. So I think we have a feel of now what the dataset is. But because the dataset is very huge and we just want to illustrate the concept of fine-tuning GPT-2 for our custom data, we are simply going to select a small subset of that particular entire dataset so that our training and evaluation processes is going to be very quick. And this is what we're doing here. Here we are selecting the first 100 samples for training, okay? And then here we are just taking the first 20 samples for evaluation. Like I said, this is just an illustration. If you have the time and resources, you can use the entire dataset, okay? So, but because we simply want to illustrate the concept, we are simply using a few of that particular sample. At this point, we can now load the GPT-2's pre-trained tokenizer as well as the model. And this is what we're doing here. This is where we are loading the GPT-2's tokenizer, and then this is where we are loading the actual GPT-2 model. So we can simply come and run this. The GPT-2 is pre-trained for text generation, and we are going to fine-tune it for summarization here, okay? Yeah, it's getting all the necessary files ready and the configuration. So it is done. Okay. So because GPT-2 does not have a padding token by default, so we're just going to set the EOS token, and that's what we're going to do here to ensure that everything runs just fine. Okay, so at this point, it is time for us to now perform pre-processing on the dataset. So here we wrote a function called preprocess function. This function defines a function to tokenize the articles as well as the summaries. Okay, and in the code you see that we are truncating the article to a maximum of 256 tokens. Okay, and the summaries to about 64 tokens here. Okay, so the summaries should be like 64 tokens, and then the articles should be 256 tokens, just for us to be able to work with this fancy data set. So at this point, we can just run this. Okay. Okay. So having run this, we can now go ahead and apply the pre-processing to the small training and evaluation dataset that we have already defined. Remember, we said we are not going to use the entirety of the dataset, okay? So we're simply going to apply this function for tokenization to the small training and evaluation data that we have already set, and this is the code that is doing that, okay? So we're setting this particular preprocess function, and we're mapping it to this particular small training dataset. We're also mapping it to this small eval dataset, isn't it? So if we do that, we are going to have our tokenized training data, and we're also going to have our tokenized evaluation data. So let's run this code now. Okay, so it has finished. Yeah, so here we have basically this is a data collator. So what it does is that it prepares batches for training and ensures padding and alignment, isn't it? So that's what it's just doing here. So we can just run the code. Okay. Yeah. And then at this point, this is where we define our training arguments. These arguments control the training process, such as the learning rate, the batch size, and the number of epochs. As you can see here, we are setting our number of training epochs to be 1, okay? And then the batch size is simply 2, and then we are also saving our results in results, okay? Here, so that we can visualize and see it later. So amongst other arguments, okay, we are also having a weight decay here. You know, it's a regularization strategy to avoid overfitting amongst many other parameters. So we can just run this. It's something we are all familiar with. Okay. So it has finished. Having set this particular training argument, it is now time for us to initialize the trainer. So there is it. We have the trainer is equals to trainer. We have the trainer class. We set all the parameters, the model, the arguments, the data collator, the tokenizer that we set, isn't it? And then basically what this is is setting up the training loop with the trainer function. So once we set this, it is now time for us to now initialize the training process, and this where we have our call for the trainer. So when we run this, we are basically initiating the training on the tokenized datasets that we have already defined earlier. And so once we do this, the training starts proper. Remember, we set our number of epochs to be equals to 1. So it's going to be very fast. As you can see, it has finished. Okay. If we make it to be more than 1, then we also see the progress accordingly. Is that okay? Very good. So as we can see, we have the training loss to be 3.24, and the metrics that we have all stated here. Okay, the number of epochs is 1. This is on a GPU, so maybe we can just raise the number of epochs to be 10, okay? Or let's say 5, just to, because I can see that it's, okay, let me make it 10, because I see that it's really very fast. So I can run this, okay? And I can now set the initializer for the trainer, okay? And at this point, I can call the trainer proper on 10 epochs because it's really very fast, so I think it can finish in good time. Yes, it's still loading. To finish now so that we can see how the training is being done as we are fine-tuning the model on this particular custom data set. Okay, we're in the second epoch now. Okay, we're in the third. Even though the training loss is decreasing, but the validation loss is not decreasing. So so most likely we're having an overfit model, but that's not a discussion for today. It's just for us to illustrate the process of fine-tuning. There are several strategies that we can put in place to ensure that our model does not overfit. But that's a discussion for another day. But here we're simply illustrating the process, and once it finishes, we are now going to so this is the 9th epoch. Okay. Yeah, it's almost going to the last epoch. Good. So it has finished, and you can see that when we raise the epoch, the training loss has also decreased. I think earlier it was more than that, and then the number of epochs is 10. So at this point, we can now save the fine-tuned model and tokenizer for future use. Okay, and so at this point, we can generate summary using the fine-tuned model, and we have this particular text. NASA's Perseverance rover has successfully landed on Mars and has begun its mission to search for signs of ancient microbial life. This marks another milestone in humanity's exploration of the red planet. And then in doing this, we can now tokenize the input text and move tensors to the same device. I ran this earlier and it gave me error, so I had to now add this piece of code in order to detect the device I'm working on before moving the model to the detected device. Okay, so once we do this, we tokenize the input text and move to tensors on the same device. Okay, and then we extract the input IDs and attention marks, and then we can now call the evaluation function. Okay, so once we do that, you can be able to now generate the summary. And remember, we said the summary should have a maximum length of 50 and a minimum length of 10, isn't it? So once we do that and we run this particular code, we should now be able to see the summary proper. Okay, so it said that the generated summary is something like this. It's not perfect because we only fine-tune on a small subset. We only fine-tune on a small subset of the data, and this is just for illustration purposes. And I believe that when we use the entirety of the data and we even have more training strategies, we should be able to get better performance results. Yeah, so I think we've already done this, so there's no need for running this. And this another now illustration of language modeling. Apart from fine-tuning, and we can just use the model as a standalone model for performing generic tasks. For example, here we're simply using the pipeline method where we load a GPT-2 model and we simply want to use it as a language model. Okay, so we want to use the GPT-2 model as a simply generic language model. So we have an input text here that says artificial intelligence is, and then we want to use this particular method, the language model generator, to be able to now complete that particular text for us. So once we do that, we run this. Let's see what happens. So it says artificial intelligence is and was able to now complete this particular sentence, having a maximum length of what? Of 20. So it says artificial intelligence is a different concept and one that many academics have been looking forward to for a very blah, blah, blah. We can also use GPT-2 for text generation. We've seen this earlier, but we can just repeat it also. So we can just have a simple once upon a time prompt, and then we can use the text generator function to be able to now generate text based on this particular prompt. And once we run this, we should be able to see the results without any problem. So it says once upon a time in a distant galaxy. This is our initial prompt. And based on our parameters that we said it should continue generating this text to a maximum length of 50. And then we have this particular very beautiful statement. Okay. And I think with this, we have an appreciation of what GPT-2 is. It's a large language model essentially for text generation. And in fact, we can do same for GPT-3 and GPT-4, even though according to OpenAI's formulation, we need to have an API key where we need to now utilize that to play around with these particular models. So at this point, we've come to the end of the lab, and I want to believe at this point, we have an appreciation of how to fine-tune a pre-trained language model like GPT-2 for performing text summarization and also performing generic tasks like text generation and language modeling.
Well done on completing today's class. Here are the key takeaways. We've seen that large language models such as GPT and BERT significantly enhance NLP by understanding context and generating human-like text. GPT stands out for its unmatched generative capabilities, representing a major leap in LLM technology. Fine-tuning allows models to adapt to specific tasks like text generation or summarization with minimal task-specific data. Pre-trained models reduce training time and resource usage by leveraging vast general language knowledge. Practical knowledge of LLMs and Hugging Face equips you to efficiently build state-of-the-art NLP applications. As always, I have prepared an assignment for you. Your task is to fine-tune a pre-trained GPT model using Hugging Face for a custom NLP task. Here are some resources for further reading, and in our next class, we shall look at sequence-to-sequence models. Thank you very much for your attention. See you in the next class.
Well done on completing today's class. Let's quickly recap the key points we've covered. We explored large language models LLMs, focusing on generative pre-trained transformers GPTs and their impact on NLP. We discussed how LLMs are trained using pre-training and fine-tuning, enabling them to generate human-like text. We also examined their applications in chatbots, content generation, and code completion. A memorable takeaway from today's session is how LLMs leverage massive datasets and deep learning to generate coherent, context-aware text, a capability that powers many real-world AI applications today. To reinforce your learning, I have prepared an assignment for you. Upload your completed assignment to the Learning portal. The full assignment details will be available on the portal. And if you have any question, Feel free to reach out through the discussion forum or Google Classroom. Thank you for your participation. Keep exploring, keep learning, and I look forward to seeing you in the next class.